Hi, welcome back. This is lecture 5. The goal of today's lecture is to introduce rings of algebraic integers. The goal for today is to introduce the ring of algebraic integers. And as usual, we'll recall some facts from ring theory. Or UFD. So this is short for unique factorization domain. And what's the definition? So suppose you start with a ring that's a domain. So suppose R is a domain. We say that it's a unique factorization domain or a UFD. We say R is a UFD. So if you take any non-zero element that's also non-unit, so if every non-zero non-unit element can be uniquely factored as a product of irreducible elements, and this uniqueness is unique up to reordering, and for each irreducible factor you can possibly multiply it with a unit and get another associate. So it's unique up to reordering and unit multiplication. Okay. Another fact is that in a UFD, an element X is an irreducible element if and only if that element is a prime element. Okay. So these are some facts from about unique factorization domains. So next proposition tells us that unique factorization domains gives us examples of integrally closed domains. So if A is a unique factorization domain, so if A is a UFD, then A is integrally closed. Okay, so what's the proof? So let K denote the fraction field of A. And suppose for the sake of contradiction that A is not integrally closed. So suppose for the sake of contradiction that A is not integrally closed. What does that mean? So that means there is an element in the fraction field let's call it alpha, that's in K, but not in A, with the property that it's integral over A. Okay, so what does it mean for alpha to be integral over A? It must satisfy a monic equation over A. So it satisfies an equation of the form alpha to the m, let's say am minus 1 alpha to the m minus 1, so on and so forth, a1 alpha plus a naught equals 0 for some coefficients am minus 1, a1, a naught that are in A. Okay, but since you have an element in the fraction field, you can write it as a numerator divided by a denominator, where the numerator and denominator belong to A. But because A is a UFD, you can write the numerator as a product of irreducible elements, denominator as a product of irreducible elements, and you can cancel off irreducible elements and get it in lowest form, so that the numerator and denominator have no common irreducible factor. So in other words, since A is a UFD, we can find a numerator and denominator. The denominator must be not 0, so that the numerator and denominator C and D have no common irreducible factor. So the alpha is this numerator C divided by D. Okay, and since alpha is not in A, the denominator D cannot be a unit. Why is that? So these elements C and D, so I should say that these are in A. So if D was a unit, then its inverse exists and it's in A. And then you see that C over D just means it's C multiplied with D inverse, but C is in A, D inverse is in A, so this product must also belong to A. But it contradicts the assumption that we began with, that alpha does not belong to A. Okay, so this element D cannot be a unit in A, it's not 0, so it must have an irreducible factor, and since C and D have no common irreducible factor, that irreducible factor cannot divide the numerator. So thus, there exists an irreducible factor, let's call it pi, that divides the denominator. Since the denominator is non-zero, not a unit, but since the denominator D and the numerator C have no common factors, this cannot divide C. Okay, so now once again, let's start with this equation. And use the fact that alpha is C over D, and substitute alpha equals C over D into this equation. What do we get? We get C to the m over D to the m plus am minus 1, C to the m minus 1 over D to the m minus 1, so on and so forth. A1 C over D plus A naught equals 0. And then once you clear denominators, what do we have? You just multiply throughout by D to the m. You have C to the m plus am minus 1 D Cm minus 1, and so on and so forth. A1 D to the m minus 1 C plus A naught D to the m equals 0. And now if you rearrange, you get that C to the m, you pull out all the other terms onto the right hand side, and you see that all of them have a factor of D in common. So you can pull out a D. So what you get is negative D, and you get A m minus 1, C to the m minus 1, so on and so forth. A1 D to the m minus 2 C plus A naught D to the m minus 1. Okay, and now since pi divides D, we have that pi must divide the right hand side, and so it must divide the left hand side as well. And the left hand side is c to the m, so pi must divide c to the m. But since pi is an irreducible element, it must be a prime element. So since pi is an irreducible element in a UFD, it must also be a prime element. So pi is dividing c to the m, but c to the m is nothing but c times c times c m times. And so this must mean that pi must divide c. Okay, this contradicts the assumption that c and d have no common irreducible factor, because we've just produced pi that divides both c and d. Okay, so this proves that if A is a UFD, then A is integrally closed. Okay. Just want to make sure that I name this proposition. Okay, call this proposition 9. Okay, let's move on. Okay, so the next topic is PIDs. So I want to recall some more facts from ring theory. So PID, which is short for principal ideal domain. And what's a PID? So suppose once again that R is a domain. We say R is a PID if every ideal of R is generated by one element. So in fact, in particular, every ideal of R is generated by a finite set, since it's generated by one element. So in particular, what this means is that if you have a PID, then R is Noetherian. Okay. Another fact from abstract algebra is that if R is a PID, then in fact it's a UFD. Okay, and so by proposition 9, if R is a UFD, if R is a PID, it must be a UFD and hence integrally closed. So if R is a PID, then R is integrally closed. Okay, and so some examples of PIDs. So Z is a PID, and its fraction field is often called the rational numbers. That's denoted with boldface Q. And if you take any field, let's call it F, then the one variable polynomial ring So this is also a PID. And its fraction field is denoted F brackets X, where the distinction is that for the ring, for the polynomial ring, you have square brackets, and for the fraction field of that, you have round brackets. Okay. Now suppose you have a finite field extension of the rational numbers, which we call Q. So suppose L over Q is a finite field extension. Then we say that L is a number field. Okay, and just observe that when you're working with rational numbers, the characteristic is 0. So the characteristic of the rational numbers and this number field L, that's 0. So this extension is automatically separable. Okay, and we can form OL, which is the integral closure of Z in L. And so this OL is what we call the ring of algebraic integers. Sometimes people just call it the ring of integers of L. Okay, so this was the ring of algebraic integers that was alluded to in the title of today's lecture. Okay, similarly, suppose you have a finite field, let's call it FQ. With characteristic P, and you take a finite separable extension of this fraction field of this one variable polynomial ring over FQ. Let's call it L, and suppose that's a finite separable extension. So we call such an F, such an L, a global function field. Okay. Okay. So let's move on to more facts. Now I'll go to facts from module theory. So suppose R is a PID. And suppose you have a module M that's finitely generated as an R module. I denoted F dot G dot. Then this module M is torsion free as an R module. If and only if M is a free R module. Okay. So in particular, if you furthermore suppose for simplicity that M is a free R module, then it's a quantity that you call, that's called the rank of M over R, and its definition is that it's the maximum number of R linearly independent elements in M. Okay. So I want to move on to our first theorem, which I'll label it 10. So suppose you have a PID let's call it A, with fraction field K, and suppose you have a finite separable extension of K, with degree n, and let's call B the integral closure of A in L, then the conclusion is that B is a free A module with rank n. Okay, so just to summarize the diagram, we have A sitting inside K. This is finite field separable extension L, and inside L this is B, which is the integral closure of A in L. So in particular, A sits inside B. Okay, and what do we have? So we have that by hypothesis A is a PID, which means that it's Noetherian, since every ideal is finitely generated. In particular, every ideal is generated by one element. But it also means that since a PID is also a UFD, by proposition 9 it's integrally closed. So by the proposition from the previous lecture, proposition 8, so we have that B is a finitely generated A module. Okay, and so it turns out that B is torsion free as an A module, and since it's finitely generated, that means it's free. Now, it's not hard to see that it's torsion free. So maybe you can ask yourself, why is B a torsion free A module? Suppose you have an element A that's not 0, little a in A, and little b in B, with A and B both non-zero. But suppose it happens that the product is 0. Now again, where is this? Where is A times B happening? This is just the usual field multiplication in L. And the 0 is just, so this equality is just taking place in the field L. But when you multiply two non-zero elements in a field, you get a non-zero element. And so this gives us a contradiction. Since in a field, the product of two non-zero elements is non-zero. Okay, so thus B is torsion free. Okay, so we have that B is torsion free, it's finally generated, so it's free. Now what about the rank? So let M denote the rank of B over A. And suppose that beta 1 up to beta m is a maximal A linearly independent set. And now since the ring B is in L and since the ring A is in K, so we claim that this set is K linearly independent. Again, why is that true? If you have a linear combination that sums up to 0, so if you have K1 beta 1 plus K2 beta 2, so on and so forth, plus Km beta m equals 0 for some K1 up to Km where these coefficients are in K. But once again, K is the fraction field of A, so each of these coefficients Ki can be written in terms of a numerator and a denominator, but the denominator is non-zero. So just by clearing denominators, we might as well assume that these coefficients Ki are in A. So by clearing denominators, so without loss of generality, and that's often abbreviated as WLOG, you just assume that all the Ki's are in fact in A. Okay, so this equation in the red box gives us a linear combination of the beta i's that equals 0, but this is a contradiction since beta 1 up to beta m is linearly independent over A. Okay, and so the only possibilities is that all these coefficients must equal 0, and since all these coefficients are 0, this tells us that beta 1 up to beta m is in fact K linearly independent in L. Okay, but L over K has dimension n. So the size of any K linearly independent set in L cannot exceed n. So since the dimension of L over K is n, so we have that m should be less than or equal to n. Okay, we are using the fact that we produce a set with m elements that's K linearly independent in L, and n is the dimension of L over K. Okay, so what we get is that the rank of B over A is less than or equal to n. Okay, now for the reverse inequality, you write, so you find a basis, say W1 up to Wn. So W1 up to Wn is a K basis for L over K, or K basis for L. And by using this lemma about clearing denominators, I think this was lemma phi in an earlier lecture, so we can find constants in K that's not 0 such that the Ci Wi is in fact integral. over A, and since the integral closure of A in L is B, they must lie. So they belong to B. Okay, so now C1 W1 up to Cn Wn, all of them are integral, so they belong to B. But these Ci's are all non-zero, and W1 up to Wn is the k basis for L. So C1 W1 up to Cn Wn, this is also a k basis for L. Okay, and hence linearly independent over K. But if you're linearly independent over K, you must be linearly independent over A. So thus is A linearly independent. Since A sits inside K. Okay, so you have a set in B that's linearly independent, and so this is only possible if n is less than equal to the rank of B over A. Okay, so on the one hand we've shown that n is less than equal to the rank of B over A, and on the other hand we've shown that the rank of B over A is less than equal to n. So combining these two inequalities, so thus we've shown that n equals the rank of B over A. Okay, so we've shown that B is a free A module with rank n. Okay, so this completes the proof of the theorem. Okay, so I want to end the lecture with some motivating questions. In the number field setting, so we have Z, its fraction field is Q, and suppose you take a number field, let's call it L, and suppose that the dimension of L over Q is n. Okay, Z, as we all know, is a PID, and we can form the integral closure of Z in L, which we called OL. So we have this commutative diagram, and what theorem 10 tells us, it tells us that OL is a free Z module with rank n. Okay, so this is some module theoretic information that theorem 10 is giving us. Is there a ring theoretic information that we can deduce about OL? So the questions are, so are there examples of OL that are not PIDs? So Z is a PID, but other examples of integral closures of L, other examples of these rings of algebraic integers that are not PIDs. Similarly, other examples of OL that are not UFDs. So we've seen that PIDs imply UFDs, and the converse is not always true. But you can ask in this setting of rings of algebraic integers, so other examples of OL that are UFDs but not PIDs. Okay. Thank you.